Welcome to this video that will be rather short, talking about the second and last activity before the summary activity in the Part A lecture notebook for Module 6. So this one is about trying to apply what we saw above with add-a-lines, which can work on data that has no gap, and using the perceptron. So here's what I would do. Create a code cell below to try learning the weights for perceptron when the data are linearly separable but without a well-defined gap as above. Comment on what you see in a markdown cell. So I'm just copying and pasting kind of what I've done above, but now this X data and Y data here have been generated with no gap. So let's go ahead and create, I would create a few code cells here, and let's say, I'm just gonna do kind of like what I did before, where I would say, now I'm gonna have new data. I'm just gonna regenerate things with the same variable names. I'm just gonna overwrite it. We're gonna have no gap. I'm gonna do something though. I hinted at this in the previous solution video, but I'm going to create with what was the actual keyword here? It was number of training. Yep, number of training equals 10. So then this will use the default with 100, and this one will use num training equals 1,000. So we'll do different numbers of training data with the zero gap. I'm just going to go ahead and write it like this, I guess, just to be explicit so you can see the difference. So 10, 100, 1,000. And as always, I suggest just to set a random seed. It doesn't always have to be the random seed. You should, in general, not always set them in a bunch of different places, but I'm just going to go ahead and set my random seed here. So I created that data. And now look what happens when I try to update things. Let's, again, we can go to just probably, 25 epochs. I just want greater control of the. In fact, I'll just do 10. 10 makes it a lot easier to use the slider than 1,000. So we'll run interact. So this is with 10 data points. So there's not much to learn from, but you see numerically there's a big gap, right? So this comes down to, again, you're generating a finite amount of data, and so it's just going to have a numerical gap, even if there's no theoretical gap. And it doesn't take too many epochs. Okay, so 2 didn't quite work, but maybe 4. 4, okay, let's say 6. Okay, at 6 it got it, right? It nailed what it is. But if you look at the comparison, look at how this learned this data, and you were to compare it, what you should really do is not just look at this perceptron, but compare it to what's going on when you're doing things with the add-a-line. So here's the add-a-line. I'll run it here again. What the add-a-line tries to do, there's no gap, it's going to try to balance. In fact, here, I'm just going to show you here. We're going to do this. So this is the add-a-line. That's visualizing the add-a-line. This is visualizing the perceptron. Here's a good comparison. Let's compare it to that X data 1, Y data 1. And then maybe not make it a markdown cell. That would be good. You should create, again, your own code cells and markdown cells to test all this stuff. But let's just compare the perceptron to the add-a-line. All right, so here's the perceptron. It took 6 epochs. Maybe it took 5. Let's just check. I think I skipped over 5. Yeah, I think 5, because 4, I don't think it worked yet. Nope, 4 was not right. You can see all this misclassification. But it took 5 epochs to go through all the data, and it's doing the right classification. Of course, it's saying that it switches over to being class 1 here, even though there's no gap. Let's look at what the add-a-line does in comparison. So, it's really far off. Let's just increase the number of epochs to, I'm going to get this down to 10 as well, just to run it so it's a little simpler. Here's the number of epochs. I'm also setting the learning rate to 1e-2. I'm not really changing that, but let's just go ahead and go up to 6 epochs. Okay, let's go to 10 then. So that looks very similar, that 10. See there? It looks, I would say it's similar to this. It's a little different. But if you were to go up to, let's say, 100 epochs, I'm just going to do this. So it's going to take a little longer to run. I'm going to go all the way up to 100. But look at what it does with the classifier. It keeps moving, right? You don't keep updating the perceptron. Once it has no misclassification error, there's no updating to it. Every time you run through the epochs, it's done. It's fixed because there's no misclassification to move it. This will keep moving. And if you look at this, what it's trying to do, let's go up to 500 epochs. I could increase the learning rate to do things faster, but there's issues with increasing the learning rates. But let's just go ahead and just give you the idea. Let's go up to 500. So it's going to try to balance the misclassification error. So there's this evenly spread data. There's 5 up here, 5 down here, and it's going to try to balance where this separation is, so that when new data comes, you have better predictive capacity with that, because it's not treating like this as the leftmost point where there's misclassification. It's going to keep shifting to try to minimize the differences between this line, where this line predicts, and what these values are. So it tries to balance things. This is perhaps again best seen if you do with some of the other data. So let's do with like x3 or x2, excuse me. So x2 is with 100 data points. Here we go, x2. Let's run this. And so you see, right, there's a lot more data now, and it took one epoch, like one run through all the data, and it basically nailed it. I'm pretty sure there's no misclassification. When I go up to 3, yeah, it's not changing this. And it's like, it's pretty much just got like, here's this where there's misclassification is. That works really well. And what the perceptron will do is, or excuse me, the Adeline, if we run this with more data, this is now with the 2 data, and we run this, and we just run that one. So with one epoch, it's not yet converged. It's going to take longer, but let's just jump it up to like 289. So it's kind of bouncing around. It takes a little longer to converge. If like the perceptron will work, it will probably converge faster than the Adeline, but the Adeline is going to try to balance the errors. And again, if you have data, if you don't have too much data where there's this gap, you would probably trust the Adeline a lot more than the perceptron, I think, because this value basically, if as soon as it was over here or it was over here, like it's just done. It's not updating anymore. And this one's going to try to find kind of the center of the gap. That's what it's going to be better at, is trying to minimize where it wants to transition between these values on an even basis. It doesn't just say like, once I have no misclassification error, I stop updating. It will continue to update. So it might be more costly, but it's probably a little bit more trustworthy. So that's the benefit. But you can see that even when there's no gap, you can still train the perceptron. This is if there's a numerical gap. So the gap in this case was 0, but because we're generating finite data, there's still a numerical gap. So it's still linearly separable. We can still do things. So this is just something that's worth playing with and thinking about. And if you're really into it, what you could try doing is editing, generating the 2D data with no gap. So this is where the Adeline is really useful. So this, in this case, here's with the Adeline. You could imagine like editing this data, how I created the training data. You could edit these boxes so that they line up and have like kind of no gap in there, and then compare as well. You don't have to, but what's really great with the Adeline is when you have no linear separability, there's a mixing of the classes. And I talk about this in the lecture. The Adeline will work. So basically, the perceptron will work if there's no theoretical gap, but they are in disjoint bins. The classes are disjoint. There's no disjointness here. The reds and the blues kind of intermingle. You cannot even use the perceptron here, as I showed in the lecture. But if they belong to separate disjoint sets, you could still numerically use the perceptron, even if theoretically there might be a problem. Numerically, it should work fine. And it might even work faster than the Adeline. But in general, the Adeline is going to try to do a better job of generalizing to unseen data than the perceptron will. So that's just worth seeing. I'm just trying to expose you to some of these like cool things that you start to see in machine learning when you do classification. That's all I wanted to say in this notebook. You should go through your own kind of experiments like what I'm doing here, set your own random seeds, and then of course just comment on what you see in Markdown. So I say comment here, so no comments. It's like half the problem is the comments. So create some data, play around with it, and just write up what you see and what you think. That's it. Thanks for listening.